All right, here it is, Friday, January 15th, 2021. Chemistry, CP, period 8. And just like the period before them, they have questions regarding the review sheet entitled Unit 3 Review, Nuclear Chemistry, Quantum Atom, Electron Configuration. And their question is about question 8, which says, write the missing isotope for the following nuclear fission reactions. And it starts off with uranium-235 plus neutron yields 3 neutrons plus bromium with atomic mass of 82 plus what? Well, let me tell you that this is something I didn't teach you this school year. And you can take this as direct evidence of the fact that being online is not the same thing as being in a classroom every day doing about twice as much time with your teacher. So I'm not going to make a big point out of teaching you this material right now because it's not on your semester final. In fact, it's unlikely that I will teach you this stuff and assess you on it this school year. But just to make a point of it, when you have an element symbol, such as uranium, the atomic number down below, represented by capital Z, is the number of protons. And the atomic mass in the superscript behind the element symbol to the left of it represents the number of protons plus the number of neutrons. When you carry out radioactive chemical processes, radioactive decay and bombardment and transmutation of elements, basically matter can't be created or destroyed. It can be rearranged. So if I have a total mass of 235 and I add to it a mass of 1, then afterwards, here's what it says on this equation. I have 3 neutrons, which have 0 electric charge and a mass of 1, 0 protons, and that. And bromine, atomic number 35, atomic mass 82, and so the question is, what goes in this blank? And the short answer is the sum of all the numbers up top on the left of the arrow has to equal the sum of all the numbers up top to the right of the arrow. This coefficient means there are 3 of these. So it's not just 235 plus 1 equals 1 plus 82 plus the answer. It's 235 plus 1, which is uranium-236, is equal to 3 plus 82 plus the answer. And it's moments like this where I pull out my calculator and say, well, so what is 236 minus 3 minus 82? And it says 151. We do the same thing on the bottom. On the bottom, and I guess you can't see what I'm writing, huh? On the bottom, I have 92 plus 0 equals 3 times 0, which is still 0, plus 35 plus the number of protons. So if I go 92 minus 35, enter, I have 57 protons. Then I go to the periodic table and I ask myself, what is atomic number 57? And the answer is lanthanum. So I'm going to put the symbol for lanthanum and say, there you go. If that's the only missing product in this nuclear reaction, then I've identified what it is. Again, a reminder, I did not teach you this material during the semester. I think it's a little bit doubtful that we will actually do worksheets and learn this material before the school year ends. I will say that there's neutron capture, there's electron capture, there's positron emission, there's beta emission, alpha particle emission. So there's much more to this than just this one example. All right, a student asked from the same review sheet how to write the electron configuration for zinc. And the short answer is, wow, okay, is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. This is called 3, not 4, even though it's on period 4. That's because of this strange Aufbau principle that says, okay, the 3D subshell is lower in energy than the 4P subshell. So it goes next. And it's higher in energy, I guess, than the 4S subshell. So there you go. My goodness, I forgot to record this. A student asked on the first review sheet, how do you find the density of a material where they give you a graph? And everyone who is in class right now just heard me work through the answer. But on the video recording, okay, the short answer is the graph doesn't obviously clearly go through the origin without question. So there could be an offset caused by the mass of a container holding this thing, or some other error with the scale. So the proper way to do this is to pick 2 points on the line as far apart as you can and write down your estimated values for those coordinates. And then from math class, do the rise over the run. So I worked it out that to me it looked like it was the point 1 milliliter by 20 grams, 6 milliliters by 111 grams. So the rise is 91 grams, the run is 5 milliliters, and density worked out to 18 grams per milliliter. The next question comes from a student regarding review sheet number 1 again, which is called Unit 1 Review Sheet. Question number 5, Part A. On this problem, they display a sketch of a rectangular solid object. Well, presumably solid, a rectangular object. Whoops, and I goofed that. And this goes about like that. And this seems to go like this. And then it goes like that, and like that, and like that. And when I do this, if I were to do it like, like the engineering students do, this would be at a 45-degree angle, actually, and they have to learn all about how to do isometric drawings. So here's the thing. This is 5A, and they give you, it says calculate the density, don't forget about sig figs, and they tell you the mass of this object is 59.52 grams. And what you notice is missing are any of the dimensions for this mass. And this is shaded, big deal. Okay, you know that the volume formula is length times width times height. But they didn't give us the length or the width or the height. So how do you solve this problem? And the answer is, well, please don't use inches, but you actually were expected to take a metric ruler. A metric ruler. And in the real classroom, this would have been a printed handout. And as you go put your ruler on a sheet of paper, you would set it up and say, so what was the length you would actually measure it? So on my crude sketch, this is 4.5 centimeters in length. And the height seemed to be 1.4 centimeters in height. And visually, it looks like it was square on the end. So you would say, oh, these two dimensions are the same. I have the third dimension. I get the volume. I solve the problem. This year, you're at home. And you might not even have printer paper in your home. And so the question came up, well, how do you solve this problem if you're looking at it on your computer screen? The answer is to have the knowledge that a standard sheet of paper is 8.5 inches wide and 11 inches in height. And as you look on your computer screen, the width of the white image, the background for this, of course, you can pinch and zoom on a lot of mouse pads and change the scale. But you need to create a scale where you can actually see the entire width of your paper at the same time. Now, if you're using a little teeny tiny Chromebook screen, that's not going to be physically the same size as if you're projecting this onto a huge big screen TV monitor, right? But what you should do at home is get the width of the white background so that you can still see it on your computer screen. And then hold your ruler up against the computer screen and set, for example, you need to measure what is the width of the white background that you see on your computer screen. This is a crude example. This is 6.2 centimeters because I'm looking on just my iPhone screen, I guess. So that 6.2 centimeters that I measure with my ruler by holding it against the computer screen scales to the 8.5 inches that the sheet of paper was originally on when this thing was drawn and uploaded. Then measure what is the size of the length of the image on your computer screen. And so in this example, I'm saying, oh, it looks like it's 4.5 centimeters. So 4.5 centimeters is to its actual length in inches as 6.2 centimeters is to 8.5 inches of width. And so if this were a valid example, I would cross multiply and go 8.5 times 4.5 divided by 6.2, enter, means this rectangle would be 6 point, call it 2 inches. Of course, you need it in units of centimeters, knowing that 1 inch is defined to be exactly 2.54 centimeters. You would then do the conversion that says, I need inches on the bottom. So 1 inch goes on the bottom. This is the shorthand symbol for inch. 2.54 centimeters on the top. Everything on the top is multiplied. Everything on the bottom is divided. The inches units cancel. And when I multiply 6.2 by 2.54, that will convert it into units of centimeters. And I have, it says 15.67. I could say I can't measure it that well, about 16 centimeters. This is not the size of that rectangle on the screen. This is an example of how you would measure the length of that rectangle on your computer screen. And then, of course, you have to measure the height. Assume that this is actually a square shape on the end and say that is 2 of the 3 dimensions. Here's the third one. Now you can finally calculate the volume and determine the density. A question from a student came up, and this one is from a review sheet. Inside its title is Unit Review, Nomenclature, Unit Conversion, and Periodic Trends. On the outside, this thing was listed as like review sheet 4. And within this review sheet, the question was number 20, which says, put the following in order of increasing ionization energy. And it lists the elements francium, potassium, krypton, and gallium. Well, as it turns out, I failed to teach you about ionization energies, although I did cover about electronegativities, and Playmata included having you play games where you learned about electronegativities. When you look on the periodic table, you can see that we're talking about francium here, potassium there, krypton way over here, and gallium way over here. And so, yikes, this is kind of scattered, right? 1, 2, 3, 4. Out of these 4, which one has the lowest ionization energy? The answer is, I didn't teach you. But just to give you a short answer, you could ask Lord Google to bring up a periodic table that is color-coded by the strengths of the ionization energies. In fact, I'm looking at one right now. And the color codes say low is, for example, where my pen is showing on the F subshells. These have low ionization energies. The bottom left corner of the periodic table has low ionization energies. Starting with boron and this column beneath it, they tend to have not quite as low ionization energies, along with tin is in this category of, well, these are a little bit not low, but they're not the lowest, but they're kind of low. As you head to helium, whoop, now you've gotten to the highest ionization energies. Kind of makes sense. Helium is so happy and so small that the last thing it wants to do is to give up an electron. And it's pretty graded here in severity. So from boron to helium, it's definitely rapidly increasing in ionization energy. For the rest of the periodic table, hydrogen is, this is a color-coded graph, so to me it looks like it's similar to nitrogen in its ionization energy levels. And as I work my way towards this column of the periodic table, these are low ionization energies, but when you finally get to around mercury, it's a moderate ionization energy, similar to phosphorus or maybe nitrogen. Okay, so wow, nothing really clearly obvious where you can say this and that. But if you had to simplify it, you would say the highest ionization energy is in the upper right corner of the periodic table, and the lowest ionization energies are in the lower left of the periodic table. And therefore, francium would have the lowest, then potassium, then gallium, and finally, whichever noble gas that was, krypton would have the highest ionization energy. Okay, an excellent question came up. Same question that was asked in the previous period. Will there be any kind of thermodynamic questions on the test? And the answer is, oh yeah, I forgot to give you a review sheet for something like that. So of course, this is a sketch of the heating curve where you're adding heat to the right and the temperature goes up on the left. And it says, starting from absolute zero, solids heat up, but then they melt, and then the liquids can heat up, but then they boil, and then the gases can heat up from there. You need to have the reference sheets handy dealing with the heat capacities of substances. So here is a reference sheet that I shared with you earlier in the semester. It has the heat equations on it, the temperature conversion formulas, and for these substances, the melting point, boiling point, specific heat in the solid, liquid, and gas states, heats of fusion, and heats of vaporization. Sadly, these are in units of joules per kilogram, and this semester we've been working in units of joules per gram. So all of these are off by a factor of 1,000. And you have the density in grams per milliliter. But wait, there's more. From the internet, sorry, wrong reference sheet. From the internet, I found and shared with you this specific heat capacity tables. And for example, it says aluminum, and out of these choices for units to express it, we've been using the rightmost unit in units of joules per gram per Kelvin. it says kilojoules per kilograms, but the kilos cancel. So this is joules per gram per Kelvin. For cast iron, it has a value of 0.554. So let's do a problem right now made up with cast iron that has a specific heat in the solid form of 0.554 joules per gram per degree Celsius. And that's in the solid state. And I'm going to say, okay, I have a mass of 325 grams. I have an initial temperature of 18.0 degrees Celsius. I want to heat this thing to a final temperature of, I can go above the boiling point of water because that's below the melting point of cast iron. So let's go to 205 degrees Celsius. I don't know if that can melt iron, but man, that's hotter than boiling water. And I ask you, so great, how much heat energy would it take to heat that mass of cast iron from this initial temperature to that final temperature, knowing that this is the specific heat of the substance? And you say, oh, this is a good, easy one. The heat I would need is the product of the mass times the specific heat times the change in temperature. So this would be 325 grams times 0.554 joules per gram per degree Celsius times the change in temperature, which is 205 degrees Celsius minus 18 degrees Celsius. Put all that into your calculator. Let's see, 325 times 0.554 times, open parentheses, 205 minus 18, close parentheses, enter. And it says that I need to clean my calculator screen. And it says 33.7 kilojoules. It actually says 33,669.35. But to 3 sig figs, that would be 33.7. Kilo means 10 to the third power joules.